So, hello everyone, it's me again. The author cannot get a valid visa in time, and I will present her work, Learning Confidence Measures by Multi-modal Convolutional Neural Networks. So, confidence measure is used to improve the disparity estimation result in stereo matching. In stereo matching tasks, many data cues can be used to design confidence measures, including input data and intermediate results, such as input RGB image pairs, matching cost values, and initial disparity maps. As shown in the figure below, the first one is reference color image, which is the left image in an image pair as default. The second one is the initial disparity map. It is achieved by directly applying winner-take-all strategy after matching cost-value computation. The third one is the error map. We consider a pixel to be wrong estimated if the disparity error is more than 3 pixels. Here, the darker red standard the higher errors. The last figure is the confidence map predicted by our method. The darker, the less reliability on current matches. Recently, convolutional neural networks have been introduced to confidence prediction, and all of them achieve better performance than convolutional ones. The state-of-the-art confidence networks only use one data cue as input, while there are other data cues used in convolutional confidence measures. We did some early experiments and found that CNNs trained by initial disparity patches had high ability to differentiate incorrect matches, while CNNs trained by reference RGB patches only have a very weak capacity. Based on this observation, we choose the reference RGB images as the second input to complement the initial disparity maps and design a two-branch CNN. There are several ways to extract and fuse the patch pair features. So first, we explore and test two basic architectures. In the early Fusion 1, we use RGB images, initial disparity maps as the 4-channel input. In the late Fusion 1, features of these two modalities are trained separately by two CNN branches without sharing weight. We found that the later Fusion network achieves the better result and performs more stable, so we choose later feature fusion. Second, to learn local information more effectively, we also try to combine dilated convolutional blocks in our basic architecture by visualizing the effective receptive fields in the basic late fusion architecture and the 3 effective architectures. It is also clear that the dilated convolutional blocks can effectively enlarge the receptive fields in both 2 branches. We also found that effective receptive fields in disparity branch are more interred while comparing with RGB branches. Our experimental results show that with only dilated convolutional blocks, the RGB branch improved the confidence performance. So we proposed a patch-based multi-modal network with dilated convolutional blocks in RGB branch as shown in the figure. We evaluate our methods on KITTI 2012 and 2015 datasets. On one dataset, 14 frames are used for evaluation and the remaining frames are used for training. We compare AUC values of the state-of-the-art learning-based method CCNN and our proposed network. AUC values of each method are sorted by ascending orders of optimal AUC values. As observed, the curves of both methods wave with a similar trend to optimal AUC values, but the gap between optimal AUC and the other two becomes larger when the optimal AUC values increase. It is more challenging to predict the confidence when the gap between optimal and the predicted AUC values grown. From the figure, we can see that the difference between our method and the CCNN method become more obvious in the ascending order of optimal AUC values. So the comparison of AUC from different methods lead us to the conclusion that our method is more robust than CCNN. That's all. Thank you.